watch the previous lecture for section 2 and 3, the end effector is moving 0.1 meter per second in the y direction. Physically, what does it mean? Anyone? Yes, correct. But yeah, thank you. But exactly, yeah, that's true. But what it means is that it's moving in a straight line. Yeah. Yes, it moves in a straight line. Okay, that's the key word that I'm looking for. It moves in a straight line. So in a way, this chapter, chapter 6, is related to the previous chapter, right? In the previous chapter, if I have a robot arm, like this, for example, right? And I have two desired end effector poses. Let's say this is the initial pose, T0, and I have a final pose of the end effector, TF. So if I want the robot arm to move begin from this pose and end up in this pose, we can design the trajectory for every joint using the 434 trajectory, for example. And in chapter 5, we do not care how the end effector behaves between these two poses. All we care is that it has to start from this pose and it has to end up in this pose. But now in chapter 6, we can make sure the end effector moves in a straight line if we want. Okay? So I hope you can see the benefit of having inverse Jacobian or using the Jacobian condition. Okay, let's move on, alright? So the Jacobian matrix for a Puma 560 robot with the configuration 0, 45 degrees, 180 degrees, 0, 45 degrees, and 0 degrees, shown in figure 5. So this is the configuration of these joint angles. We have this Jacobian matrix. It is 6 by 6 matrix. And if you want to achieve end effector motion of 0.05 meter per second, again in the y direction, so this is x and this is y. So if I want the end effector to move in this direction at 0.05 meter per second, I can compute what is the required joint velocity. Okay, so we have to, of course, you have to compute the inverse and then multiply with 0, 0.05, 0, 0, 0, 0, and you get this value. Okay, so if we actuate your joint velocity to be this vector, that means theta 1 dot is 0.0037, theta 2 is theta 2 dot is minus 0.0009, and so on. You can achieve 0.05 meter per second in the y direction. All right. So can we just inverse, right? We need to compute the inverse. Okay, the first condition is satisfied. It is a square matrix, 6 by 6 matrix. Condition 1 satisfied. Condition 2, it has to be non-singular, right? The determinant of J has to be non-zero. So we cannot always achieve that. We cannot always achieve condition number 2. It depends on the configuration of the robot. For a certain configuration, we cannot. J becomes non-singular. J becomes singular, which means the determinant becomes 0, as we will see shortly. Okay. I have a question. The V is 0. What is this? Are you answering something? The previous question, I think, right? Sorry, what are you answering, Muhammad Fikri?
The answer for the page 19.
Answer for page 19.
How the V is 0 and 0.1 and 0.000.
Yes, exactly. Okay, good. Yeah, you asked me that question, Fikri. Let me show you in MATLAB, okay? Because this is 6 by 6. I cannot. Good question. So in MATLAB, of course, in the toolbox that I asked you to download and install, it has its own Puma 560, but with a different DH parameter because they use a slightly different convention. So in order to tally with our chapter 4 and so on, I had to build my own Puma 560. Okay. So I've shown you this earlier, right? In order to build your own robot using the toolbox, first you have to define your DH parameters. You don't have to define theta because theta depends on the configuration, right? Theta I. But you need to provide DI, AI, and alpha I. So if you remember, can I ask you a short quiz question? I mean, just a question test to test your memory. So how do we get this D, A, and alpha? DI, AI, alpha I. How do we get? Or what does it depend on? What do they depend on?
Coordinate frame of this joint when we compute.
Exactly, right? So yes, very good. So first for every link of our robot arm, we would establish a coordinate frame according to the DH representation. There's an algorithm, right? Which will be given for your test and exam. So using that algorithm, the DH representation, you will establish one coordinate frame for every link of your robot arm. From the established coordinate frame, you will come out with the DH parameters. So we have DI, AI, alpha I. Okay, good. So this is the DH parameters, and then you call a function called serial link, and you have to, inside that function, you have to call another function called revolute, indicating that you are having a rotary or revolute joint. And then you save your robot as Puma. Okay. Let me comment this out. Control R, Control T is to uncomment. Okay, so I've built my robot. The name is Puma. I want to give a configuration. The configuration is this one, right? 0, pi over 4, pi, 0, pi over 4, 0. And then there's a function in the toolbox called Jacob 0. There's the Jacobian matrix. That means you can compute the Jacobian matrix by providing the configuration, all the joint angles. So this is my QNS. I provide it here. I can invert the Jacobian matrix by calling a MATLAB function called INV. And then I multiply with, like our friend what's his name? Like Muhammad Fikri says, yes, it's indeed 0, 0.05, 0, 0, 0, 0. Where is it? Here, right? 0, 0.05, 0, 0, 0, 0. Okay? So let me show you. So this is the configuration. Okay. And this is the Jacobian. It's the same as in our notes. If you want to compare it. Okay, minus 149, minus 625, 320, 000, and so on, right? And this is the joint velocity. Again, we can compare this with our notes. 0.037 minus 0.09 and so on. Okay. All right. Okay, good so far. Let's move on to Jacobian Singularities. So like I said earlier, at a certain configuration, the determinant of a Jacobian matrix will become 0. Okay, and a robot configuration theta is a vector, right, at which the determinant is 0 is described as singular or degenerate. So indeed, mathematically, when determinant of a matrix is 0, we call that matrix to be singular, right? If the determinant is non-zero, in mathematics, we call that matrix to be non-singular. But in robotics application, there's a phenomena called, or event called singularity. So singularities occur when the robot is at maximum reach, or when one or more axes become aligned, resulting in the loss of degrees of freedom. And this is what we call the Gimbal Lock problem. For example, at the Puma's ready pose, so this is the ready pose, with theta 1 to be 0, theta 2 is minus 90, theta 3 is 90 degrees, 3, 4, 4, 5, 6 is 0 degrees. At this configuration, J becomes singular. This is our J, this is our Jacobian matrix. If you try to compute the determinant becomes 0. Let's check in MATLAB. Okay, this is the ready pose. Okay, this is the Jacobian, and we can compute the determinant, right? The determinant of that matrix. So J Puma, this matrix is J Puma, and it is the Jacobian matrix at the ready pose. This is the ready pose. So the determinant is 0. So what that means at this configuration, my Jacobian matrix becomes singular. So we cannot compute the inverse of J. So this is what we call the Gimbal Lock problem. So looking at the Jacobian, it is clear that columns 4 and 6 are identical. That is, two of the wrist joints, joint 4 and 6, are aligned. Alright, so one way of looking at this is you can see that joint number 4 and joint number 5, they will produce the same spatial velocity. Okay, what that means is that there is a spatial velocity vector that we cannot produce from this configuration. Okay, it's a bit hard to imagine or understand, but all you have to know is that to make things simple, whenever J becomes singular, right, the determinant is 0. Physically, what it means is that you would lose some degrees of freedom. That means there is a spatial velocity that you cannot achieve from that configuration. Okay, let me try to draw it and try to explain, okay? Let's say, how do I explain this? So let's move to another problem, okay? Let's say you have a car. So this is x-axis. This is x-axis and this is y-axis. And you have a simple mobile robot. So this mobile robot has rear wheel which cannot be steered and front wheel which can be steered. Okay, but the engine or the motor of this robot is situated at the back. So this is the motor of the robot. Okay, so this is the motor. The motor is driving the rear wheel, and the rear wheel cannot be steered. This can be steered. And let's say the spatial velocity of this robot arm is Vx, Vy, and omega z. Alright. So what that means is that you can steer the robot in. So this is the spatial velocity, right? So whenever the robot moves, it has three components. It has x velocity, y velocity, and the angular velocity. Okay, but there is the configuration. So this, if I want to map this in a three-dimensional space, I can map the velocity, right? Let's say if I want to draw this vector, so this is Vx, this is Vy, and this is omega x. So for a certain value, this is a vector. So this vector can be maybe 1, 0, 0. Right? So 100 means Vx is 1 meter per second, Vy is 0 meter per second, and omega z, sorry, this is omega z. Omega z is 0 radian per second. But there is a configuration of this robot where we would have a problem. Right? For example, let's say now the robot becomes like this. So let's say the wheel somehow becomes rotated to the extreme, right? So you can call this maybe 90 degrees. So what happens here? The motor is at the back. If the motor is at the front, maybe it wouldn't be a problem, right? But the motor is the back. The motor exerts torque on the rear wheels. So you can imagine the rear wheel is trying to spin, but the front wheels are steered 90 degrees. So we will not have any motion in this direction, right? In fact, nu will become 0, 0, and omega will become 0 as well, right? There will not be any motion at all. Okay, so this is the case where I say the determinant of the Jacobian will become. So if you perform a calculation, you will get the determinant of this Jacobian will be 0. Alright, so in this configuration, if you try to compute the inverse of the Jacobian matrix, you cannot compute because the determinant will be 0. And what that means is that there is a spatial velocity that you cannot perform. So and physically you can see that you will not have any motion. Okay, so there is a point here where the robot cannot achieve. So the robot cannot have, so the robot cannot achieve any velocity here, right? It will not able to have any velocity from this configuration. So if you want the robot to move like this, for example, right? This is nu equals to 0, 0, 1. So you will not be able to achieve this in this configuration. So that's the problem with singularity. Okay, so as much as possible we want to avoid robot singularities. Alright, so this leads to the loss of 1 degree of freedom, since motion of these joints results in the same Cartesian velocity, leaving motion in one Cartesian direction unaccounted for, as we can see early here, right? So in this configuration, joints 4 and 6, they will cause the same spatial velocity, and what that means is that you will lose 1 degree of freedom. However, if the robot is close to but not actually at a singularity, we encounter problems where some Cartesian end effector velocities require very high joint rates. At the singularity, those rates will go to infinity. So we can illustrate this by choosing a configuration slightly away from the previous data, which we have just showed was singular. So this is the configuration where we have where J becomes singular, right? Where we had the gimbal lock problem. So if I move slightly away from this configuration, so if I add 1 degree here, right? See in the fourth joint, instead of 0, I have 1 degree. The Jacobian now becomes this, and it becomes non-singular. All right. If you try to compute the determinant is non-zero. And to achieve a relatively slow end effector motion of 0.1 meter per second, so if I take the inverse of this and I compute and I multiply with 0.100000, I have a very high speed motion of some joints. Okay. In order to have 0.1 meter per second in the x direction, my joints have to be very, very fast. See, 1 multiplied 10 to the power of 29. So to give you a feel, it's the same thing here, right? I'm not sure if you can imagine this. Perhaps if you have ridden your bicycle, you can imagine. So in this case, no matter how hard you push, your robot will not move, right? Without breaking the front wheels. But if we move slightly away from that configuration, let's say slightly away, right? Let's say this is 85 degrees, for example, right? So now, if you push your motor hard enough, you can probably have some motion, right? You can see the robot will turn, right? The robot will turn. The robot indeed will turn and move in that direction. So your nu becomes non-zero. Okay, so in this configuration, you will not have any motion because this is what we call the gimbal lock. And if you try to analyze the Jacobian matrix, the determinant is 0. In this configuration, slightly away from the singularity, right, if we have your wheels to be at 85 degrees, if you push your motor hard enough, you can have some non-zero motion. You will notice that the mobile robot will turn, and it probably will move in that direction, in that x and y direction. So here, if you analyze the Jacobian, the determinant will be non-zero. But of course, the catch is your motor has to work really, really hard to produce some motion. So this is not in gimbal lock situation. This is not in singularity. This is in singularity. So similar problems we can have in robot arm. Okay. In this configuration, we can have the gimbal lock problem where we will lose some degrees of freedom, which means there is a spatial velocity, or there are some spatial velocity values that the robot cannot perform or cannot achieve from that configuration. However, if you move slightly away from the singularity, like this, you can achieve all the spatial velocity, but the joints have to take a toll, right? They have to actuate the joints really, really hard. And in other motions, if we, for example, if we wish to rotate the tool about z-axis, okay, so now using the same configuration, using the same Jacobian matrix, if I want only to rotate in z direction, the joint rates are very modest. We don't have a problem. So it only affects in some spatial velocity values. So this particular joint configuration is therefore good for certain motions, but poor for others. All right. So I think that's all for today. I want you to try to understand first what we have learned so far before I move on to the next topic, resolved rate motion control, because or else it'll be too much for you to digest in one session. Okay, so please, in your own time, watch this video again. If I upload it, I will upload it later, and ask me questions in the next lecture. Okay, and in the next lecture I will answer your questions if you have any, and I will proceed with the resolved rate motion control. Okay, so before we move on, do you have any question today so far?
Digesting.
Okay, all right. It's okay. I will try to show more examples in the next lecture for better understanding. So now let's look at your tutorial number 5. Just going to give you a guide if you have any problems. So before I talk about it, have you tried tutorial 5? Do you have any question for me? Not yet, huh? Okay, never mind. I'm sure you have many things to do with your time. I understand that, but your test is this Friday, right? And yeah, anytime you have question, you can ask me on WhatsApp. I will try to answer as quickly as possible. So tutorial 5, let me just give you a brief overview of what it's all about. If you notice, it is similar, well, it's same, it's very, very close to what we have in the notes. So question 1, explain the importance of designing robot arm joint trajectories by including the position constraints in your explanation. Of course, you can think of a clear answer for this, right? So why do we need to design a robot arm joint trajectory? Because we want it to move, we want the end effector to move from one given a pose to another pose, right? And it says including the position constraints. So there are 4 position constraints. We have initial position, we have lift off position, we have set down position, we have the final position. Okay. All right, so if I have an object to be, this is just a repetition, okay? Is there a question somewhere? I wonder how to solve 6 by 6 later on. What is this? Is not a question, right? This is just your thinking to yourself. I'll just leave it. So this is let's say we have an object to be picked. Okay, this is an object, and the object has some kind of fixture or something to hold this object at its place. So this is a fixture, and this is the object to be picked. So I need to pick this object from here and place it somewhere else. Maybe I want to place it here, right? Okay, I want to paste, and again we have a fixture here as well. So I want to pick an object here and place it here. And because I want to do that, I need to have my robot arm to start from this pose and end up in this pose. And this is exactly why I need to design a trajectory. So this is the importance of having a robot arm trajectory, because I want the robot arm, the end effector of my robot arm to be in to begin in one pose, position orientation, and end up in another pose. And we have to design the H1, H2, H3 for every joint. So let's say I have 3 joints here, right? 3 joints. So I need to have my H1 of T for joint number 1, H2 of T for joint number 2, and H3 of T for joint number, H1 of T, H2 of 3, H3 of 3, H3 of T for joint number 1, and I have to design again H1, H2, H3 for joint number 2, and I have to design another set of H1, H2, H3 for joint number 3. Okay, so that is the to answer that question, right? The importance. That is why it's important to design a trajectory, because we want the end effector to move from one pose to another pose. And we also want it to move in correctly, right? We just don't want it to move, right? We want it to move correctly and safely. So the key word here is correctly and safely. Correctly and safely. So what do we mean by safe? So it has to pick an object and move safely away from the fixture. So that is why we have a number of position constraints. So I have the initial pose, lift off pose, I have the set down pose, and the final pose. So these are the position constraints. Okay, so of course you can make your own sentences and lines and paragraph figures to answer this question. All right, question number 2. A Puma 560 is used to pick and place an object. The required pick and place end effector poses are given by HTMs T0 and TF. So this is the end effector's pick or initial pose, and this is the end effector's final pose or the place pose, right? Remember, pose is position orientation. The question says, from inverse kinematics, you can compute this using this, right? Using this and inverse kinematics, you can compute this. Inverse kinematics we have learned in chapter 4. And similarly, using TF and inverse kinematics, we compute this. These are in radians, not degree. And the question says, design a 434 trajectory for joint number 1 with lift off position given and set down position given for joint number 1. Remember, right? The first subscript refers to whether it's initial position, set down position, lift off position, final position. Subscript number 2 refers to the joint. Okay? And in this question, you have to sketch the designed joint trajectory and label clearly all the relevant information. So we have done this in our previous chapter in class, during class. Of course, maybe I did not sketch it, but the sketch is even given in the notes. So nothing different there. But then question 3 requires you to perform the calculation. You have to do you have to compute this using inverse kinematics. You are given the arm configuration indicators. Okay, you have to, and then question 3b, you have to compute this using inverse kinematics. Of course, you can check, right? If you, from your computation, if you get it to be this answer, that means it's correct. And then you have to show the lift off pose and the set down pose can be computed to be this. So we have, here you are given the lift off position, and this is computed using inverse kinematics from the lift off pose. And in question C, you have to actually show how you can compute T1, the lift off pose, to be this matrix. You have to show. Then D and E, you have to draw the various poses to show the importance. And in question F, you have to compute the lift off position, which is this one. You have to compute this. Okay, how can you compute this? Of course, using T1, which is given, and inverse kinematics again. Okay, and question 4 is quite similar, but with some twists here and there. All right, I think you can do it, no problem there. So please try in your own time, and if you have question this week, you can always ask me. Okay, do you have any question for me now? If you don't have any question, that's all for today. I will see you again on Tuesday. All right, thank you very much.